unfortunately, we don't have time, and we have to move for the third talk by Pires, again on isolated neutron stars and hopefully future observations with the eROSITA.
Okay, hello everyone. It's a pleasure for me to be here today. I'm Adriana Pires from the Leibniz Institute for Astrophysics, Potsdam, and I'm here to talk about our expectations for the population of thermally emitting neutron stars to be detected by the eROSITA survey. I would like to acknowledge the work of my collaborators, as well as the eROSITA German consortium. So, the neutron stars we observe are dominated by pulsating sources of radio pulsars, and 50 years after the discovery of the first pulsar, over 2,600 objects are now known, and these mostly come from radio pulsar surveys. They are divided into two main groups, as we know: the canonical neutron stars, rotation-powered pulsars, and the millisecond fast-spinning pulsars, which are thought to be recycled in binary systems. There's also a growing number of radio transits called RATs that are being detected by dedicated searchers in radio pulsar survey data. And only about 2% of the observed population consists of peculiar groups of X-ray emitting stars, which I will concentrate on my talk here. So thanks for the very, very good overview given today by Samar's talk, and also other people in this conference. I don't need to spend much time to talk about the phenomenology of these different groups of neutron stars, in particular the X-ray emitting neutron stars, magnetars, the group of nearby cooling neutron stars discovered by eROSAT, which I call here Magnificent 7, and CCOs. It's only important for me now to stress that these objects completely escape radio and gamma ray pulsar surveys. And yet they do, their properties challenge our understanding of neutron star emissivity and evolution. So the question is, do radio pulsars tell the whole story? Let's have a look again at the PP dot diagram of isolated neutron stars. So the standard picture of pulsar evolution tells us that neutron stars are born rotating very fast, and they will evolve along lines of constant field towards longer periods until the pulsar is not energetic enough to create pairs of positron electrons that are responsible for the radio emission. So until a certain point, the pulsar is not detected in the radio wavelengths anymore. And this is what more or less radio pulsars tell us in a broad sense. Now, when we add the peculiar source to this diagram, we see there's something that starts to not fit completely on this simplistic scenario. First of all, magnetars are up there, where very highly magnetized neutron stars should be. The Magnificent 7 are located more or less intermediate between magnetars and the bulk of the population. And indeed, the Magnificent 7 do show, in a smaller scale, properties that are similar to magnetars, in the sense that they have also brighter thermal emission and also long spin periods. And finally, CCOs, the three CCOs which we know, P and P dot, are in this part of the diagram, which is important to notice that is very scarcely populated. So the question is, if there is no field evolution of these objects, we should see evolved CCOs, old CCOs in this part of the diagram. And we don't. Radio surveys and X-ray surveys, people were trying to see their descendants around this area of the diagram, and we don't see them. So, again, that's something that goes against the standard picture. Now, to understand that, let's have a look at how fast a neutron star cools down. This, again, shows a simplistic view of a cooling diagram, cooling age diagram. This shows the age and temperature of rotation-powered pulsars with bright enough thermal emission. And we can see that they pretty much follow the standard picture. However, when we add the other sources, the X-ray emitting neutron stars, we see straight away the magnetars, and in a smaller scale, the Magnificent Seven are just too hot to be explained by standard cooling. And also CCOs, we also see these saw these during this conference. They seem to require a light element, the presence of a light element, accreted envelope or envelope to explain their higher temperatures for their kiloyear ages. So it's clear that it's actually because we know the magnetars in particular and the M7 exist, and that's from X-rays, that we are beginning to understand the important role of magnetic field decay at producing hot and long spin period neutron stars. And also the observation of CCOs, and here I just put a few references. In the past years, this has really pushed ahead a different outcome of neutron star evolution, where we believe that these neutron stars are young, but recovering from an early episode of fallback accretion after the supernova event, which is responsible for hiding their magnetic field deep into the crust. So that would explain the anti-magnetar behavior. There's the fact that they are not detected as radio pulsars, but also that the cooling rate may be affected. This could explain why evolved CCOs are not on this part of the diagram, but should, at some point after the field diffuses back to the surface, be found among the rest of the population. So it's clear it's the magnetic field that governs the neutron star phenomenology. In particular, its strength at birth, whether it decays or grows during the neutron star lifetime, and the effects that these have on the neutron star rotational and thermal evolution. And in particular, how the neutron star will be detected by us, the neutron star visibility across the electromagnetic spectrum. It's important to stress here that those channels, those evolutionary channels, are not probed by the bulk of the population, the radio pulsar population. And also they are not predicted by theory. Despite the big progress that was done in recent years, it's also important to stress that even the state-of-the-art models of field decay are built over uncertain assumptions concerning, for instance, the initial field configuration and also the level of impurity of the crust. This completely determines how much energy will be deposited in the crust and the cooling curve of the different neutron stars. And what's crucial is that, as it is, the observed population of pulsars, including radio and X-ray objects, is not sufficient to constrain those models of field decay. This is shown by the work of Goulon and collaborators of a few years ago. Likewise, the phenomenology of CCOs has triggered a lively debate over their formation and fate. And however, we do not know the fraction of neutron stars in our galaxy that do undergo such an episode. And also, can we ever hope to constrain the time scale of field reemergency. We detected the descendants of CCOs later on among the rest of the population. This is determined by the amount of matter that can be accreted on the neutron star. And there are many conditions that can prevent this to happen. I just mentioned, for instance, deviations from spherical symmetry, neutrino-driven explosions and convection in accreted envelope, as well as this neutron star spin period or even the spatial motion. So this is not known from theory what can really prevent fallback accretion to occur, and also the level of field submergency. So the question is, are those alternative scenarios rather ordinary? And if not, what are the consequences to the birth rate of neutron stars in our galaxy? And of course, we also want to be able to explain within this unified picture this transitional behavior between different objects, different classes of neutron stars. So, okay, this grand unification of neutron stars is really waiting for us to know more about X-ray emitting neutron stars. They are not detected in the radio and gamma rays. So progress will only be achieved when we can extend our knowledge towards fainter fluxes. So we only know so far the X-ray bright end of the neutron star population, either from the ROSATs, the very nearby ones, or when they go through outbursts. So we do need to obtain a better sampling, discover and then characterize the evolutionary state of those individual sources in order to evaluate the impact of these alternative scenarios on neutron star evolution and detectability. So that's where we hope that eROSITA can step in. eROSITA is the next all-sky X-ray survey mission that will be launched hopefully next year in September. It's a Russian-German collaboration, and it will scan the all-sky 8 times in 4 years with unprecedented sensitivity, angular energy resolution. It will detect millions of Xray sources, and these will require, identification campaigns will require a very crucial synergy with large-scale multi-wavelength photometric and spectroscopic surveys and facilities. But we believe that eROSITA has the unique potential for the next decades to come to really unveil the faint end of the neutron star population and hopefully help us to understand the population as a whole. So in order to create a forecast for eROSITA, we developed a model, population synthesis model, where neutron stars are born from progenitors distributed on in the spiral arms of the galaxy. After the supernova explosion, the neutron star evolves in the galactic potential while cooling down, emitting soft X-rays. So it's very important to also model the absorption from the interstellar medium. We take this into account. And also the survey properties in order to compute the number of neutron stars that would be detected above a certain limit. And then we compute Monte Carlo simulations of this model to obtain average properties. Here on this plot, I show the eROSITA effective area for 2 different configurations of optical blocking filters, which is still not decided. In comparison with XMM Newton PN, I hope you can see here, and ROSAT PSPC. And here is the eROSITA sky exposure after 4 years of the survey, which is very concentrated along the ecliptic poles. So our simulations give a number of up to 100 neutron stars to be detected through the thermal emission after 4 years of all-sky survey. Their distance are within 400 parsecs and 8 kiloparsecs, with a median of 2 kiloparsecs. Their exposures within 1.6 kiloseconds and 8 kiloseconds, and the faintest neutron stars in our detected sample are of the order of 10 to the minus 14 ergs per second per centimeter square. That means that eROSITA will be 50 times more sensitive to neutron stars than ROSAT BSC, the Bright Star catalog, was. And around 30% of the sources will be brighter than 10 to the minus 13. Here I show the log n log s curves from our simulations for these two different configurations of optical filters. Now, to dig these neutron stars from the millions of Xray sources that will be detected by eROSITA is not going to be an easy task. We will rely on heavy cross-correlation and cuts in X-ray color space, visual screening, and optical and infrared follow-up. And here, to illustrate, I just show our past work with the 2XMMP catalog of sources, where from our original sample of flux-limited sources of 72,000 sources, we selected 30 good neutron star candidates for follow-up. This eventually led to the discovery of one neutron star with a purely thermal-emitting neutron star in the Carina Nebula, which we have been studying ever since. Here's our expectations for follow-up. So with our simulations, we can compute the limiting magnitude that will be required for each neutron star in our sample so that we can rule out AGN and CVs in particular. So this will be based on X-ray to optical flux ratios and requiring a minimum flux ratio of over 1,000. The median magnitude required for identifications is of the order 27.4. So that means that the sources at intermediate flux can be already follow up in the immediate aftermath of the survey using current facilities. So here's already the summary and outlook of my talk. We expect of the order 100 of neutron stars to be detected in the eROSITA Xray Survey, which will be of the order of 50 times more sensitive than ROSAT was. The sources at intermediate flux can be followed up with 4-meter and 8-meter class telescopes in order to rule out AGNs and CVs. XMM Newton, as well as eROSITA during its pointed phase, which will follow the survey phase, the 4 years of survey, will be required to search for pulsations and eventually spectral lines, understand the energy emission of these neutron stars. Chandra will be equally important for sub-arc-second precision to search for diffuse emission and pulsar wind nebula, for instance. And of course, we need to also search for counterparts in the radio and gamma ray domain. These all require to really tackling the evolutionary state of these neutron stars in the hope of then evaluate the impact of these alternative evolutionary scenarios on cooling. And of course, we expect in the long term that the next generation of optical telescope, the extreme large telescope, SST, Athena, and SCA, will help us to identify even the faintest neutron stars in our eROSITA sky. Here, leave you with the slide from Bob Rutledge 6 years ago in the first eROSITA International Conference, which, although some scaling maybe is needed on these numbers, conveys the very, very important message that we still have many neutron stars to discover in our galaxy. So, thank you.
Questions? Bettina.
I was wondering, looking at the response of the eROSITA, it seems to be more sensitive towards higher energies in contrast to ROSAT. So I would think that you probably are likely to detect more hotter neutron stars than, say, the Magnificent Seven. Did you look into that?
Yes, of course, that makes sense. But it actually is more sensitive at the energy band where we expect to find the most distant ones, the fainter ones. So those will be exactly on this energy band. So, of course, for the nearby ones, there is a bit of a sensitivity factor that is lost when we compute the numbers for the whole population. The ones that we want to detect, the ones beyond the solar vicinity, are the ones that eROSITA really can make a difference in respect to ROSAT.
So we will likely find similar sources like the
as well, of course, okay. Yes.
I have a question as far as we have this picture. So just 2 telescopes out of 7 will have soft sensitivity. Is it true?
It's a bit complicated. There are 2 detectors that have built-in chips, and this means that they can be operated with or without external filters. So in my simulations, I consider 2 different configurations, which means when they are all the 7 with external filters, which is the more conservative scenario, or when they are open, those 2.
Okay, and this uncertainty, 85, 95,
yes.
It's mostly related to this fact, or?
Yes, on the number, yes. If you look at the properties of the detected neutron stars, the very not significant difference between the 2 samples with 2 different optical blocking filters.
Okay, other very urgent questions? Then let's thank the speaker and all speakers of the session and enjoy your coffee and tea.